Rock and roll. There we go. 6.2. 6.2. So, in the previous section, remember we were simplifying trigonometric expressions. And in 6.2, we're going to do the same thing, but we're going to have a definitive target instead of just some vague notion of where we're supposed to end up. We're doing trig proofs, baby. This is everyone's favorite time of year. Earth Day, spring, trig proof time. What's that?
What?
Earth Day? What? Birthday. Amanda's birthday, not Earth Day. It is Earth Day.
Birthday.
Yeah, it's the day the Earth was born. It's the day Amanda was born. Probably in different years.
Birthday.
Probably in different years. What year was the Earth born? How old is the Earth today? 12, probably. 12 gazillion, right? All right, 6.2, trig proofs. As we set off on this great adventure together, consider one of my favorite quotes of all time by the mathematician W.S. England. This is kind of like the idea, the philosophy that you need to incorporate into your trig proof activities, okay? Mathematics is not a careful march down a well-cleared highway, right? Like on The Walking Dead, the zombies always, when they travel en masse, they take the roads, right? Roads are good if you're in a hurry, right? But not if you're a pioneer, not if you're a trailblazer, a trendsetter. So instead of a careful march down a well-cleared highway, which is pretty much all of your experience in school, it's always been a well-cleared highway. All the problems have been given to you. They've been designed so that they work out relatively nicely. But in real life, math is a journey into a strange wilderness where the explorers often get lost. And it's okay to get lost, right? That's kind of in the part of the adventure. You have to persevere. Rigor should be a signal to the historian that the maps have been made and the real explorers have gone elsewhere. All right? So you're not traveling with a map. You just have some tools. You have some algebraic tools, and you got some identities that you've memorized, and your mathematical machete is either your stylus or your finger, right? And using that mathematical machete, you're going to hack your way through the strange wilderness onto bigger, better places. Okay, so we've already kind of talked about this, so let's go ahead and get another toe-dipping example, right? Which we know what that means now. Prove the following identity. Okay, so prove the following identity. This is kind of, in a sense, a well-cleared highway in the sense that you already know in advance that it's supposed to work. The left side is, in fact, equal to the right side. In real life, you might have two expressions like this, and you don't know if it's an identity. So you might plug in specific values to verify. And remember, if it's true for several values, then you might have an inkling that it is true for all of them. Unless you find one value that doesn't work, then you know it's not an identity. So you're never going to have to decide if something is an identity or not. You're going to be told this is an identity, but now you have to prove it. Okay? So it's like a manufactured wilderness for y'all. Step one is to draw a line down the equal sign. And what that's supposed to do is to prevent you from, working on both sides at the same time, like adding two cosines squared. Once it is an identity, feel free to manipulate it however you want. But in the process of proving it, you have to work each side independently. And because they're expressions, they have to remain equivalent. So every line that follows is equivalent to the one above or below. You can do some of the things we talked about in the previous section, right? You can expand if there's something to distribute or FOIL it out. You can factor. That's another good thing. You can combine fractions by getting a common denominator. You can divide out common factors. You can combine like terms. You can add a clever form of 0, and you can multiply by a clever form of 1. Those are the algebraic things you could do. And then, of course, we also know we can make replacements with something that is equivalent to it for all values in the domain, namely an identity. So those fundamental identities that we quizzed over on Thursday, you can use those as well. And the goal is to make the left side look like the right side. So it doesn't matter which side you start on. You can actually work on both sides. If you get stuck on one, jump to the other. And as long as the bottom lines on both sides are equivalent, you've created a logical loop of statements that completes the proof. And then, of course, at the very end, you can write QED, or you can sign off like Happy Monday. Good morning. Oh, yeah, yeah, come on in. Come on in. Oh, that's still stuff for me. You can set it right there. Yeah, yeah, yeah. Thank you, guys. I appreciate that. Yeah, and then that big box, you can just sit down right there. I was going to go get that later, but you guys are too kind. I appreciate it. Have a good Monday. Oh, that's all my stuff that I loan the seniors, all my reject camping gear for their campsite. Yeah. All right. And then at the end, you write QED, or you sign off with your name or something. All right. So in the spirit of what we talked about last time, building up or tearing down, remember it's easier to tear down than build up. So you want to start on the side that you perceive to be, bless you, more challenging looking, possesses more information. But ultimately, there's no wrong side on which to start. So which side would y'all like to start on, left or right? Left? Yeah, most people would say the left because for two reasons. It has two trig terms instead of just the one trig term on the right. And notice the powers. This is kind of important. The powers are higher powers. And higher powers, like 4 versus squared, they're like a denser nucleus. They have more information built into it. All right, so what could we do on the left? The right side is now our target. So notice I want to keep the cosines and get rid of the sines. I can use Pythagorean identities to relate sine squared to cosine squared because I need to pick up another cosine squared. But I can't use the Pythagorean identities yet because things have to be squared. And right now I have it to the 4th power. So what to do, what to do? Anybody see anything on the left side? We can expand, we can factor, or we can factor maybe. Possibly, that's one. Can we factor the left? Maybe. This is a difference of what? 2 squares. Now, how do we know it's a perfect square? It's not 2nd power, but it's 4th power. Those are even numbers. And if those are even numbers, they're perfect squares. Because remember, taking the square root of something is raising it to the 1/2 power. So remember that the difference of 2 perfect squares will factor into the product of 2 what conjugates? Conjugates. Good. So let's go ahead and set up our factors. The square root of sine to the 4th is what? What's the square root of sine to the 4th? Sine to the 2nd. Good. You just take half the power. Same thing with cosine. So we know one of them is going to be sine squared plus cosine squared, and the other one is sine squared minus cosine squared. Plus and minus, or minus and plus. It doesn't really matter. So it's the square root of the first term, square root of the last term, and then 1's plus, 1's minus. That gets the middle signs, the middle terms to cancel. All right. So notice that's good because now we have squared powers. Now, if you were to write a reason off to the side, it would be factored. But we don't have to write reasons as long as we show every single step. All right. So the right side is still our target. Anybody see anything now? Whoopsh, 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 whoopsh. Stop it. Leave me alone. Whoopsh. He's slapping you in the face. Look at me, right? Yeah, there is Papa Pid. That's Papa Pid. So that's 1 times sine squared x minus cosine squared of x. The reason would be Papa Pid. Now, what's 1 times anything? Itself. So if you want to just go to a separate line, you can drop the parentheses now because now we just have an expression. The reason for that would be identity element of multiplication. So remember, in a proof, if there is a doubt whether to include the step or leave it out, what should you err on the side of? Leaving the step out or putting it in? Putting it in, right. Okay, because the process is the product. If there would be a reason, you need to show the step. The reason would be identity element of multiplication. All right, so now the right side is our target. Notice we have a cosine squared, we have a cosine squared. That's fantastic. Well, we only have one of them on the left. We need to pick up another one. We need to have 2 of them on the right. And I also need to get rid of sine squared. So how can we get rid of sine squared, and simultaneously, I guess, pick up another cosine squared. Can we write sine squared in terms of cosine squared? Yes, a la Papa Pid. So let's put parentheses around that. Sine squared is what in terms of cosine squared? Again, these are the ways I told you you're probably going to be using them. Cosine squared plus sine squared is equal to 1. So if you bring this across, sine squared is equal to what? 1 minus cosine squared. That's real helpful to kind of know, all right? So that's going to be 1 minus cosine squared. And the parentheses there show the substitution. There's really nothing to distribute out front other than a 1. So really, we can drop the parentheses. And when we drop the parentheses, you don't have to show that as a separate step. I can combine like terms. What's minus cosine squared minus cosine squared? Minus 2 cosine squared of x. Compare that to the right-hand side. Do they look the same expression-wise? Yes. Yeah, they do. So that completes the proof. So then we say whatever we want down here. Happy birthday, Amanda. See, there you go. Exclamation point. Now, is that the only way to do that proof? No. There are other ways. There are, other ways that maybe are more scenic, require more steps, but if that's how you see it and that's how you do it, that's fine. There are different roads that lead to San Antonio, and some of them take longer, some of them are more scenic, some are more direct, but as long as we get our final destination, we're good. All right, any comments or questions on that? Did you like that one? Look for factors. Okay, so if we're going to extract strategies, this one would be look for factor opportunities. Factoring is a strategy. Okay, and you have your perfect square trinomials, you have your difference of squares, common factors, all that good stuff. Okay. All right, let's move on then to number 2. Oh, there it is. There's the summary. Factoring. Common factors, difference of squares, perfect square trinomials, difference or sum of 2 cubes, which we'll see one of those near the end. So that's one of the strategies. We'll kind of make a summary statement after each one of those. All right, prove the following identity. You know it's an identity. You know it's supposed to work. Draw a line down the middle, and on your marks, get sets, go. Give this one a try. All on your own. All right, you got your mathematical machete. Venture off into the strange wilderness. Anybody want to volunteer the side you started on? Left or right? They kind of look equally complicated, right? Because there's two trig functions in each of them, but on the left there's two terms, and on the right there's two factors. So, question, is it easier to combine two terms to get one term, or is it easier to split up two factors to get two terms? It's usually easier to get a common factor and combine two terms than it is to decompose, we say, into partial fractions one factor. So in that sense, the left side is probably a little bit better. Now, I say combine two fractions. We don't have fractions on the left, do we? There you go. So that's a strategy that not only works when you're stuck, but sometimes from the beginning. If you put everything in terms of sine and cosine, remember that's the genetic DNA that all trig functions are made up of. So that would help. Sine of x over cosine of x plus cosine x over sine of x. All right, cool. Now I have non-trivial denominators in fractions. So the LCM is their product, right? Cosine times sine. So if you want to do your crisscross applesauce here, that would work. Or you can multiply the first one by sine over sine and the second one by cosine over cosine. I'm going to do the crisscross applesauce. So remember, you got to start in the top left. Sine times sine is sine squared. Take the middle sine plus, then the other diagonal, cosine times cosine is cosine squared. All over the product, or the common denominator, cosine times sine. All right, are we making strides towards our target? Yes, we now have a single term. The right side is a single term. Okay, cool. Now reassess. Take a look at it. You see anything? I see 1, 2. Sine squared plus cosine squared. There he is again, Papa Pid. That's 1. So that's 1 over cosine x times sine of x. Now at this point, you may get stuck, right? You may be like, well, what to do? So is it okay to jump to the other side? Sure. Notice the left side is in terms of sine and cosine. Let's do that on the right side. Secant is 1 over cosine times 1 over sine. Do we need a common denominator to multiply two fractions? No, you just multiply straight across. 1 times 1 is 1. Cosine x times sine x is cosine x sine x. Does that look like the left side? Yes. Now, if you had in the denominator sine times cosine on one side and cosine times sine on the other, would you be done? No, you'd have to commute the factors. The reason would be commutative property of multiplication. So make sure that it looks exactly the same, but for maybe a color difference and a font difference. They're the same. So you can actually sign off whatever, easy. So that would get full credit. Now, if you are kind of wanting to stay on one side, this shell tells you what your next step could have been on the left side. Okay, just work straight up. So this could be 1 over cosine times 1 over sine. And now, of course, 1 over cosine is secant, and 1 over sine is cosecant. Okay, so that gives you the same thing. Then, if you want, you can come back and erase the right side, and now it's all on one side. But it doesn't matter. It's entirely up to you, as long as both sides on each side are the same. So if you ever have like a bunch of work over here, you start working on this side, it doesn't match up, and then you figure out how to do it, and you don't want to erase, just draw a line through it like that. Or better yet, just draw like a horizontal line through all the work. And that makes it invisible to the graders. That would be me, yeah. Quote unquote invisible. That's an AP thing too. If you just draw a line through text or numbers, the AP readers don't grade it. Okay. So there's always like for AP exams, there's always like something nationally on social media where it say, write something on your test, like, why so serious was one of them one year. That appeared all over the AP exams, and then there was a line through it. Like, they're not allowed to grade it. So, and then there was another one, a different year that said, "We are Sparta," and then there was a line through it, and it's like, hee, they can't grade it. Yeah. So anyway, there are better things to do, right? All right. Any comments or questions on that one? All right. So here you go. When all else fails, get everything in terms of sine and cosine, and combine terms by getting a common denominator. And you can also add this strategy: work on both sides. Work on both sides. We better say this word: independent. Then let me see. Independent. That's a long word. Independent. That's 5 syllables. Holy moly. Don't you like when people use acronyms for phrases, but the acronyms they use have exactly as many syllables as the phrases they represent? Like, be right back. They say BRB instead. It's like, how is that any shorter to say? BRB. Be right back. They're both 3 syllables. You're not really saving anything. But people do that, right? I don't know why. Anyway, IDKW. I don't know why. See, same thing. If I say IDKW, you're like, what the heck is he saying? But if I said I don't know why, you're like, oh, he doesn't know why. And it's the same number of syllables. But if you're like saying like work on both sides independently, now you could say WOBSI, and people are like, oh, that's a lot shorter. WOBSI, right? That's only 5 syllables total versus like, wow, 1,000 if you say it all with real words. Work on both sides. Here goes 5 independently. So WOBSI. Yeah. WOBSI. Wobsy. Yeah, you can cut 5 syllables down to 2 then. When you just say Wobsy. Work on both sides independently. It's a lot shorter to say Wobsy. All right. Any other questions? I don't know how that one came up. Stylized acronyms don't even have the dots, do they? In fact, you can write that as a word. I think if I ever get another dog, I'm going to name it Wobsy. When I get another dog. The 2 dogs I have are still young. They're not going to die soon. So maybe in 10 years I'll get another dog, and I'm going to name him Wobsy. Because I've been wanting to name a dog Archimedes forever, but my wife is like, we are not calling a dog Archimedes. I said, how about one of our kids? No, no, no. Have you met my daughter Archimedes? What? Would Wobsy be a boy or a girl? A boy? Wobsy. Wobsy? Is that a real thing, Wobsy?
Yeah, it's a video game.
Oh. Huh.
It's on Nintendo 64. It's like a bootleg game that I didn't know was a bootleg game.
Oh.
When I was a little kid, I played it, and it's terrible, but I didn't know that.
You know what would be weird is if you named one dog Wubsy and the other one Wobsy. You'd really have to enunciate when you call them, otherwise they're both going to come. Right? No, 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 Wubsy. I called Wobsy. What's that? Oh, yeah, yeah, yeah. Come on, Wobsies. All right. Did he call you or me? I don't know. Let's both go. All right. Yeah, yeah. Yeah, I'm recording. I'm recording. Wobsy. That also reminds me of the other thing from the youth. George, you might have heard, right? Fuzzy Wuzzy. You like that? Yeah. Fuzzy Wuzzy was a bear. Fuzzy Wuzzy had no hair. Fuzzy Wuzzy wasn't fuzzy, was he? All right. Okay. Number 3. Prove the following identity. I'm going to let you have a chance to look at it on your own. I'll help you out by drawing a line down the middle. You're welcome. You have to still draw your own line, but that should be the first thing you do. All right. See if you can get that one done. Oh, God. He was reunited yesterday with his Wubsy, wasn't he? Yeah. The empty tomb, and he went back to heaven. Oh, Easter. Yeah. I don't even know if Jesus' nickname was Wubsy, but for that reference, it was. Yeah. You know, it's another funny thing. My dad's dog that I had for a while, his name was Zeus. And so we'd call him, "Hey, Zeus, come here." And he's like, "My name's not Jesus. It's just Zeus." You know? And so, "No, hey, Zeus, come here." And so as a joke, instead of "Hey, Zeus," when his real name was Zeus, we kind of sometimes called him Jesus. You know, because Jesus is Jesus in Spanish. Yeah, so Jesus. It's like, me llamo no Jesus. Me llamo solo Jesús. All right, Jesus. Yeah. Mm-hmm. All right. Anyway. Mm-hmm. What side should you start on? The left. Same reason on the previous one. These are already fractions. It's two terms. The right side is one term. So get a common denominator. Let's make sure we're all on that route. If you do your crisscross applesauce, whatever, your butterfly multiply, it works great because the common denominator is their product. So 1 times that is that. I'm not even going to show the 1. Plus, now this is important. If that were a minus, you'd have to be very, very careful on the next product. But because it's plus, there's really nothing to distribute. So plus 1 times that is just that itself, secant x minus 1. If that had been a minus, you'd have to distribute the negative. All over their product, which is secant x minus 1 times secant x plus 1. And yes, we are making progress because the right side is one term and the left side is now one term. Now what? Do any obvious math? Anything good happening in the numerator? Your 1's are canceling, right? But your secants are doubling. So we got a 2 secant x. Now, look at your right side. You're like, ooh, I got a factor of 2, I got a factor of 2. I'm not messing with the 2, right? I'm halfway home, baby, right? I got the 2 like I needed. So I'm not going to mess around with that 2. All over. What can we do in the denominator? Secant x minus 1, secant x plus 1, minus plus. Those are conjugates. The product of two conjugates gives you a what? A difference of squares. And when there are actually powers of 2, that sets up a Pythagorean identity. Okay? A difference of squares coming from product of two conjugates will usually set up a Pythagorean identity. You're going to get secant squared of x, the inside and outside cancel, and you're left with minus 1. And now you're like, sweet. So notice we still have 2 terms in the denominator. I would really like it if it were a single term. So, in your mind, secant squared minus 1, that's the same as what? Tangent squared. Good. Because 1 plus tangent squared is equal to secant squared. You can solve it. Bring the 1 across. Secant squared minus 1 is tangent squared. So you get 2 secant of x all over tangent squared. Nice. Now you look at the right side and you're like, okay, it's looking good. It's looking good. So could your next step on the left then be 2 cotangent of x cosecant of x? Would that be the proof? Would that be good? Is that obvious how you went from the second to last line to the bottom line? Nope, not at all. I'm like, what happened there? Magic? Okay. So what could you do at this point?
Tangent and secant and cotangent cosecant.
Yeah.
Uh,
What would you do?
see if there's something with inverse.
Yeah. What could we essentially do to both sides? We can put it in terms of sine and cosine would not be bad at this point. So that's going to be 2 times 1 over cosine, and then tangent squared is sine squared over cosine squared. Okay, so this would be a point where I'm not sure how it condenses down. So if we do that, now we have state change flip. So really 2 times 1 over cosine is 2 over cosine times cosine squared. And we flip it over sine squared. And now what happens with one of your cosines? The factors. They divide out. So really we're left with 2 cosine x over sine squared. Now, because that's in terms of sine and cosine, what can we do on the other side? We can do the same thing, right? That's 2 times cotangent is cosine x over sine of x, times cosecant is 1 over sine of x. If I now multiply straight across, I'll have 2 over cosine of x, all over sine squared of x. Is that what I have on the left side down there? Yeah, right? So, B-I-O, bio. Now, B-I-O has 3 syllables. You know what it stands for? Bring it on. Bring it on. Right? Now, when you say B-I-O versus bring it on, same number of syllables. But when you write B-I-O, it's a lot shorter to write B-I-O than it is to say bring it on. But you might lose people. Bring it on. Now, if you wanted to go all the way on the left-hand side, all you would have to do is on your next line below on the left, you would have to do that. That would be associating your factors in a different order, and then you could do that. So you could kind of put those 2 lines on the left side and complete it on one side. But there's nothing wrong with jumping to the other side. So eliminate complex fractions. That's something you should always do. As soon as you create one, be like, my next job is to get rid of it. And put it in terms of sine and cosine. All right, I think that's all that we have time for today. So I hope you had a good time, as much a good time as I did. And we'll see you all again tomorrow. It's a beautiful day in the neighborhood, a beautiful day in the neighborhood. Won't you be mine? Won't you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in the neighborhood with you. So let's make the most of this beautiful day. And since we're together, we might as well say, won't you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Please won't you be? Please won't you be my neighbor? Goodbye, neighbor.